Okay, so, dear colleagues, in the world and in the room, thank you very much for giving us this great opportunity to present our recent research on Bayesian reasoning before this eminent community. Actually, the two of us, we're kind of newbies in this business. We are familiar with the basics, but we, from our background, Katharina, as an educational psychologist, of course, knows about Bayesian methods, and me, as a math educator, knows about the Bayes rule and the curriculum. But as a cognitive tool or as a research framework, we haven't used it yet. But we entered this new area of Bayesian cognition only recently when doing research on teachers' diagnostic judgments. We have a larger community of doctoral students who work on this, and when we saw that diagnostic judgments are nothing but doing judgments with the goal of reducing uncertainty, it was clear that it's about Bayesian reasoning in some way, and we tried to convey this, what we did with this insight in our research.
Okay, so as Timo said, we study Bayesian reasoning in the context of teachers' diagnostic judgments. And therefore, we constructed, to give an example, a task that is similar to the very familiar Bayesian reasoning task, textbook task that you all know in this context. Let's say within fifth graders, one has a 15% chance to encounter a student with a whole number misconception about decimals. This is actually a very, very common misconception in decimals, which all math educators will know. So such a student usually, with a chance of 95%, gives a wrong solution to the comparison task and says 4.125 is larger than 4.7 because he or she reasoned that 125 is larger than 7. Also, students with a sound understanding of decimals give this wrong solution with a probability above 20%. A teacher sees this error during class, and he or she usually addresses the misconception directly when the chances are over 50% that the student has a whole number misconception. Should the teacher take action? Well, to all of you, the structure of the task should be very familiar and only new at the context, teacher's judgment, and maybe the focus on the decision and not the posterior. We say that it's plausible to use such a task in the context of teacher education when students are learning the Bayes rule. However, in the context of real teacher diagnostic judgment, this is somewhat artificial. We argue that in contrast to this task, when teachers judge the misconceptions of their students, these numerical values are not present in the situation, nor in the teacher's mind. So we claim that it's more realistic that the reasoning is non-numerical. That is, the data is noisy and there's no arithmetic processing. And also, teachers usually have pictorial support. So without the numerical information, the task reads like this. One has a small chance, such as student usually, or he gives this wrong solution with a small probability, and so on. We think that it's plausible that teachers have such kind of information, because they may have approximative knowledge about the prevalences of the misconceptions, either from literature or from their own experiences, and they also may have knowledge about the sensitivity and the specificity of tasks from their experience in many cases. And in our work, we investigate plausible processes for updating the judgment, the probabilities in the context of diagnostic judgments. So our general framework for diagnostic judgment that we use in the larger research group is this one, where we model the process as information processing. The evidence, the response of a student to a task. And that allows to infer student knowledge, this misconception. And the teacher entered the situation with diagnostic knowledge. The prior probability, prevalence, small chance, and the conditional probability, a student with this misconception usually solves the task incorrectly. And our main question is, in order to arrive at a decision, what are adequate models for the information processing? Can this be modeled by Bayesian reasoning? And actually, the context for teachers is even more complicated. Usually, there's more than one misconception. So, in the case for decimal, there are three very, very frequent misconceptions. And therefore, we designed a non-numerical environment with three hypotheses. So the three misconceptions, that would be three different diseases in the medicine context. And these are represented by the three corners of this hypothesis space, which we call Hypothegon. And for reducing complexity at least a little, here we only model students with a misconception. That is, we have no, so to say, healthy students. That is, the teacher knows all of the students here have problems with decimals, but they don't know which misconception they have. So the three misconceptions are the whole number misconception, the ignore decimal point, and the shorter is larger. A student with the whole number misconception considers the number before and after the decimal point as whole numbers and says 4.8 is smaller than 4.63 because 4.8 is smaller than 63. The student with the ignore decimal point ignores the decimal point as it's already in the name and argues 4.8 is smaller because 48 is smaller than 463. And a student with a shorter is larger misconception considers the number of digits after the decimal point and argues 4.8 is larger because it has only one digit. So, given this reasoning, students with the whole number misconception or the ignore decimal point misconception usually enter the task compare 4.8 and 4.63 incorrectly. This is indicated by these likelihood bars. So you see a large proportion of red over here indicating the probability for a wrong solution. But still these students may solve the task correctly occasionally, maybe due to a lucky guess or because they already know the numbers, which is represented by the green part. And the other way around, the students with the shorter is larger misconception usually solve this kind of task correctly. And here in our study, we set the likelihoods to 20 and 80%, displayed by the red and green parts. In addition, the three misconceptions have different prevalences. In the population modeled here, the whole number misconception is the most likely one, and the shorter is larger misconception is the least likely one. This is represented by these bars at the prior position and also by the position of the point. The closer it is to one of the corner, the more likely this misconception, the higher the prevalence of this misconception. So in this example, a student answered the task correctly. do the teachers do? We assume that the teacher has all information. It is displayed saliently in our presentation. And he or she uses that information to update his assumption on whether the student has, which misconception the student has. So to update the probability, one has to move the point within the hypothesis space. Closer to a corner means higher probability for this misconception. And this is an example how we investigate Bayesian reasoning within teachers' diagnostic judgment, which is the focus of our talk. We divided our talk in two research interests. First, we aim to capture non-numerical reasoning and detect Bayesian reasoning or bias strategies. And second, we discuss a cognitive plausible heuristic and test whether it can approximate Bayesian reasoning. But let's start with the first part. So, how did we capture non-numerical reasoning processes? We designed the Hypothegon that I just introduced, and it presents the hypothesis space with all relevant information. Given the selected prevalences and the likelihoods, a specific response to a task, like here, a right response to this task, one can calculate the posterior with a Bayes rule. That would be this green dot over here. That would be the judgment according to the normative Bayesian reasoning. And we wonder, do teachers come close? Do they systematically deviate? And how can we infer the underlying information that they use? How can we infer biases? And as a background to these questions, we analyzed known strategies in Bayesian situation with regard to the type and amount of used information. So the correct application of the Bayes rule requires all of the information, the likelihoods of all alternatives and the Bayes rate. But then there are also strategies that ignore information, like the ones that neglect the prior probabilities, often called prior neglect, which you all know. And these only focus on the likelihoods, either only on the likelihood of one hypothesis or the likelihoods of all alternatives. And while there are different variants of these strategies, we dub them as single evidence and combined evidence strategies, as we only focus on the type of information used. In addition, some research has found a strategy that only considers the priors. So following this strategy, people do not update their judgment at all despite the evidence. However, a prior-only strategy seems less likely in our context, as teachers generally focus on and react in numerical settings, also be detected in a non-numerical setting. Therefore, we use the Hypothegon as an environment for assessing the strategies. As already said, the teachers have to judge which misconception a student likely has, and he or she knows that all students here have problems with decimals. They just have to decide between the three misconceptions here. On top you see the names of the students. For each student, we present one task and one response. That is, we study single Q judgments. And the task and responses differed per student. We systematically varied the evidence, as shown here. So each type of task, with 3 different types, has a specific pattern of most likely response given one of the 3 misconceptions. And as each task can be answered either correctly or incorrectly, we have 6 cases. And we presented each case twice. So teachers have to come to do 12 judgments. Does not hit a point as evidence for the use of one of the strategies. We argue that the closer a point is to the calculated point, the higher the likelihood that the participant applied this strategy. That is, the likelihood that the participant applied one strategy decreases with distance from the calculated point, which we modeled with the Gaussian distribution. And the circles presented here represent areas of similar likelihoods in 10% percentile steps. So for each judgment, we calculated the likelihood of the judgment given a strategy for all three strategies. And then we updated the probability for the teacher's judgment for the 6 cases. So here you see 2 cases. In the first case, the judgment strongly contributes to the BUS strategy, it's close to BUS, and not so much to the other strategies. In the second case, the judgment contributes to the posterior of the SES strategy and somewhat to the CES strategy and only little to the BUS strategy. And finally, after the 6 cases, after the 6 updates, we compared the posterior of the most probable strategy to the second probable strategy. And the logic is that when a subject consistently uses one strategy in all 6 cases, the evidence should lead to a considerable increase in the posterior of this strategy and a decrease in the posterior probability for the other strategies, resulting in a high certainty for the classification. So on a meta level, we apply Bayesian reasoning at different levels. We did not investigate Bayesian reasoning on the student level, but we modeled a probabilistic connection between the latent thinking, the specific misconception, and the manifest behavior of the student. That is the response to a task with the likelihoods 20 and 80%. We investigate a Bayesian model of information processing on the teacher level, because this is our main research question. Do teachers use Bayesian strategies or do they use other strategies? And on the researcher level, we use Bayesian classification for classifying strategies. So, what did we get? Can we distinguish the different strategies at the teacher level? So, yes, we can. Overall, the certainty of classification was high. We see only for 3 participants that the evidence for the classification was weak. All of which were classified either as CES or as SES. And this is not too surprising because we selected the likelihoods and the priors in a constellation that clearly allowed us to separate BUS from the other strategies. And the CES and SES always were closer together, which we already have seen here. So the BUS strategy in both constellations always farther apart from the other strategies. So it's kind of not surprising that the cases where we couldn't clearly distinguish between the strategies are always strategies, the CES or the SES strategies, the evidence-only strategies. More importantly, the evidence for the classification was strong and mostly even extreme, the Bayes factor of over 1,000, that for the vast majority of the participants. So we see we had a high certainty for our classification. Now, can we detect all strategies? The answer again is yes. Our classification allowed to detect all three updating strategies. In the non-numerical setting, BUS, CS, and SES, but we see only a small number of participants using the BUS strategy. When we have a closer look at the data and the distribution of the different strategies across the participants of the two conditions, we see a small tendency that participants who received an additional instruction on the relevance of using priors and likelihoods process more information. That is, we see more BUS and less SES for these students. And that was actually a second research question in our paper. In a different area of teachers' diagnostic skills, not Bayesian reasoning, it has been shown that highlighting the relevance of integrating different types of knowledge significantly improved the integrated use of the different types of knowledge. And therefore, we thought it's reasonable to argue that such an instruction on the relevance of integration could also be useful, beneficial in the context of judgments with Bayesian reasoning. So our question is, does instruction on the relevance of using all probabilities, priors and likelihoods increase the processing of more information represented in the non-numerical setting? So how did the relevance instruction look like? In addition to the prompt to use all information, which was the same in both conditions, the participants of the relevance instruction condition received more verbal information on the integration of the information, but without providing the solution. And at the end, the instruction was summarized as shown here. So first look at the priors, then look at the fitting likelihoods, and finally also at the likelihoods of the alternatives. The instruction purposely did not include an example of the procedure in order to avoid superficial copying of the updating strategy. So we've already seen the descriptive data over here. The relevance instructions seem to slightly process more information. However, the Bayes factor suggests that there's only anecdotal evidence for an effect. In the paper, we consequently only reported the Bayesian analysis, but yes, also the chi-squared test fails to reach statistical significance. So to conclude, we presented all information in a salient way. We instructed participants to use all information, and yet they did not. Why did we fail to increase Bayesian reasoning in contrast to the many studies that you guys have conducted that succeeded in increasing Bayesian reasoning in numerical settings? So let's have a look at the most common approaches of supporting Bayesian reasoning in numerical settings, using frequencies instead of probabilities and using visual representation. So how do these approaches support the correct Bayesian posterior? As we've already discussed yesterday and today, if likelihoods are presented as joint frequencies, the priors are already contained in the joint frequencies. So of the 10 people who lie, 8 have a red nose. And thus, deriving at the correct posterior is computationally simple, an aspect that is only relevant in numerical settings. Adequate visualization, such as the unit square, increases the salience of the multiplicative prior likelihood interaction and the size of the areas over here already provide the results of the multiplication. Thus, in contrast to our relevance instruction, previous successful support show the result of the interaction of likelihood and priors. And against this background, we devised a visual representation of the prior likelihood interaction in our non-numerical setting and investigated its effect in a second study. By scaling the length of the likelihood bars in relation to the size of the priors, the multiplicative nature of the prior likelihood interaction is explicitly shown, and similarly in the unit square, it allows to compare the absolute length of the likelihood bars as direct representation of the posteriors. So here you only have to compare the size of the green parts of these bars. So the research question obviously was, does a visual explication of the prior likelihood interaction in the non-numerical setting increase the processing of the information in the sense of Bayesian reasoning? And we compared the condition with the visual explication to the control condition of study 1. This time, the difference of the distributions of the strategies is more pronounced. And indeed, the analysis showed a high Bayes factor, providing strong evidence for the effectiveness of the visual explication. And for the sake of completeness, yes, the chi-squared test was significant. So to summarize this part of the talk, we identified all postulated strategies in the non-numerical setting. And the certainty of the classification of these strategies was strong. With regard to the different conditions, well, the salient representations of all information in our non-numerical setting in the control condition was not sufficient for correct Bayesian reasoning. And also the additional relevance instruction was not very effective. Only when converting the information to display the interaction of priors and likelihoods, similar at the unit square, correct Bayesian reasoning was fostered, which matches previous studies in numerical settings. So, what did we learn? Well, by modeling the situation in a non-numerical way, we also tried to avoid the normative framing of mathematically correct statistical reasoning. And we say, well, overall, the hypothegons seem to be an effective setting to present and investigate probability information for updating judgments. However, the impact of the geometric nature of the hypothegon on the reasoning process remains unclear, as we did not include any different representations in our studies. With regard to the biases and strategies, we showed that the common strategies from research in numerical situations persist in non-numerical situations. However, in our experimental framework, we instructed the subjects with respect to the intended interpretation of the external representation, and we did not investigate their mental reasoning processes. In this aspect, the focus on the mental reasoning process is something we will put more emphasis on in the second part of our talk, but before that, we would like to discuss this first presented study. So, would you like to discuss?
And please forgive us when our answer is we will tell about this in the next part. Maybe we have some solutions to your questions, but maybe you have questions for this study which is complex enough to discuss.
So are you opening for questions?
Yes.
Or
For the first part, yes.
for this part? Okay, I've been asked to comment on it anyway, so let me start with it. And first of all, thank you very much for a very interesting presentation. And I read your paper carefully, and I was very impressed. Yeah. And I think it can open new pathways to for new directions for studying Bayesian reasoning, in particular because, I mean, that for me it was the first time that I saw a study investigating Bayesian reasoning in a non-numerical context. Yeah. And you started out with a with investigating diagnostic judgment of teacher or teacher students, and in mathematics education that's a very important important issue. It's an important professional skill and knowledge of a mathematics.
We do too.
And yeah, I mean, your whole setup is, for me, I had to read it several times to get the ideas, yeah, and so it's not something like that you read 10 minutes before you go to sleep, yeah, at night. Yeah.
Would you?
Yeah, I must say I'm now a bit confused. I thought there would be a talk and then there would be two discussions. And then in the middle you suddenly said this is our first part, and the second comes later, and now we discuss. And I didn't know whether this was a public discussion or whether it's already...
We don't either. So if you have hints for this part we just presented, just go ahead. And we will, otherwise we proceed to the second part where we...
I mean, I'm prepared, I could say something as a discussion, but and I can say this now.
Do it now.
Yeah, but chances are that I could also say this afterwards, and there would also fit. I'm confused whether this is now my slot as a discussion or whether this is a general thing.
Feel free to decide.
Yeah.
Okay, good. So then I just...
The second part.
Good. So then I just give comments based on what you now said. On the one hand, I found it very interesting and inspiring, and on the other hand, I'm also a bit confused. A bit confused about what is the Bayesian task here. So one thing I heard that you had students, and the student had to solve a Bayesian inference task, and that you also looked into non-numerical presentations. This is the one way to make sense of what you said. And the other way to make sense of what you said is that students had a task, namely to compare two numbers, 4.8 and 4.763, and then there's the chance that a student will say 4.63 is larger than 4.8, that's the mistake, and then you wonder, okay, what can explain that the students make this mistake, and then you come up with three hypotheses, and then the teacher is asked the student, what was the reason why this student made this mistake? This is, I would say, not a Bayesian inference task for a student, but it was a Bayesian inference task for a teacher, and the material was not a Bayesian inference task, but a number comparison. And here I'm confused what your Bayesian thing is.
Completely natural that you're confused, because when we do teacher education research, we always have these levels, and we mix up these levels. So the student level, it's really comparing decimals. It's fifth graders. It's not Bayesian. They simply try to solve an arithmetic task, and they fail with a certain probability, so we can model it by probabilistic means, but it's no means Bayesian. On the teacher level, it's Bayesian. It's going from evidence, inferring from evidence on hypotheses about the students. Sometimes we say students, we mean teacher students. So the teachers we investigated, to confuse you even more, are students of ours learning to diagnose students.
So you can understand why I was
totally.
Now I feel better. I thought it was my side, or only my side. Okay, good. So then I continue based on this. I continue with this Bayesian task that the teacher said, who was wondering why did the student make this mistake. So the first thing that comes to my mind is, of course, why is this interesting at all? So a student made a mistake, and of course as a teacher it would be good to have a mental model of the student to understand what a student understands so that I can correct the student. So from a practical point of view, I would say this is not super relevant, because I as a teacher have my class, I explain numbers and comparison, and I did this, and then I say, dear students, here's the homework, and please compare blah blah blah, and then I give this out, and then I go home and read what the students do, and then I see all kind of things, and occasionally I say, oh gosh, who explained this to them? And oops, that was me. And I see all kind of mistakes, and then I go back to class and sort it out, and have to say, sorry, obviously I didn't do a good job, I have to explain it again, and then I would go through this again. What I would not do is, okay, you guys made 3 types of mistakes, and I at home classified you. That was a complex Bayesian inference task. I'm not going into this, I just present you the result. You made mistake number 1, or had the wrong conception number 1, 2, and 3. And now you guys go out and I explain to them and explain it to you what you should have done. No? And then you made this mistake and now I explain it to you. In practice, I think this is completely irrelevant. No one would do it, I would not do it. So this classification task may be nice to say, here guys, we found a new application for Bayesian inference task, but I think in practice, I don't see the relevance.
This problem that this may be artificial, what we're doing. But we have to ask whether there are, in respect to teachers' activity,
okay.
not in respect to Bayesian reasoning, in respect to what teachers do on a regular basis. And the first case of teachers doing class instruction, of course, when I only ask about my class, I'm not interested in the individual student's problem. Somehow it's the whole class I have to somehow instruct and really tell the story. Okay. In the case of diagnosing individual students, it's totally different. It's not.
Oh, sorry, guys. Can you on Zoom hear what he's saying?
Oh, sorry. So I come a little closer.
Maybe ask whether if they already said it, heard it, then there is no way.
Did you understand me until now?
Hands up whether you understood him what he said so far.
Okay.
Gets it now. Okay, so the micro was good enough.
Yeah. So the situation we describe is a situation of a teacher, let's say, go around in the classroom, observing students when solving tasks, and recognizing a certain error. And now the teacher has to decide, what am I going to do? This is an error, but maybe it's not relevant to react already because it can be by chance. Or this error, what does it indicate? Which kind of misconception may the student have? And then there's a big ambiguity. Since every single task never tells the story. A single task can be, any of the errors, you have seen the table with right and wrong, any of the errors can be done for several reasons. When I know that, I can see, I have 2 errors that are probable, two hypotheses, 2 misconceptions that probably lead to this error, 1 doesn't. And now I have to decide between these. Of course, not by multiplying likelihoods with probabilities, but by combining this information. This is a very frequent error and a very frequent misconception, so let's do something. It's useful to do something. Or this is an error, but the misconception is very rare. I have to look for a second time. It's not time to go to every student doing this error. So this is the regular situation, doing individual diagnosis and asking for on-the-fly reaction.
Okay.
And this is quite usual in cases when the errors are known. Most of the errors for most of the content in math education is not as well known as decimal comparison.
And you don't just want to correct the response, but to address the misconception. And so your instruction or your explanation would be different depending on which misconception the student has.
Good. So then let me continue with my comments. The other comment is reliability. I as a teacher would be interested in the reliability. I would not just look at one mistake, but I would try to understand whether there's a pattern. I would like to see more examples and basically do exactly what you did in your table, where you had the 3 hypotheses and then this 3 numbers. The other was 3.02 compared to 3.0 or so, and then you had this, I would say it's an experimentum crucis, and then this is like if it is this misunderstanding, they would get this right and these 2 wrong, and with this misunderstanding they would get that, and so on. So this would be an experimentum crucis, and here I would, by the way, also like to introduce this natural sampling idea. So these numbers are constructed, selected in a certain way to have this experimental crucis. What you could also do is you could randomly generate a left number, a right number, and then have these hypotheses, and you can simulate this just by an algorithm. And then you have, for an infinite number of comparisons, these three hypotheses who would generate whether they get it right or wrong. And then you would have kind of a natural frequency table and see how many, or what's the, Then you have this matrix that would also allow you to predict, if you have this misunderstanding, how many of the comparisons you would get right or wrong. But this is the one direction. If understanding, what's the mistake? Your direction is something else. If mistake, what's the understanding? Okay. So here I think this is also a useful way to look at this and to see to what extent or how this is a Bayesian reasoning task. And I would now like to make a link to a paradigm, and we have an expert here in this room, and the expert is Stefan Kraus, and the question is, spontaneously, I ask you, or you all guys, and then I tell you what I see here. How is this linked to the Monty Hall problem? So, for those of you who don't, what? Do I have to explain what the Monty Hall problem is?
How long do you need?
Yeah?
How long will it take?
Do you know what the Monty? Of course. Okay. Anyone who does not know what the Monty Hall problem is? Okay, so there are three doors. You know that behind one door there's a car, between two there's a goat, and then you open one, and then Monty Hall, do you want to change? Huh? Okay, good. So everyone knows. So what's the link?
Are you still asking whether we don't know the problem?
No, I'm not asking whether you know the problem. I'm asking what is the link to their task.
Please tell us.
Hans-Jörg.
You can construe it as a Bayesian reasoning task involving a perspective change.
Yeah, this is the solution. It's a Bayesian reasoning task. This is a link. Perspective change is a solution how to understand what the right probability is. But still, what is the link to this task? Okay, so here's what I see. You have three hypotheses. These three hypotheses relate to these three understanding what is the misconception. And Monty Hall has three doors. So now you have a particular comparison, 4.8 and 4.63, and you come up with three hypotheses. This could be the misconception, and all three misconceptions could lead to the correct understanding of the model of the student. Corresponding to three doors, and behind each there could be the car. Now you get an update. Monty Hall tells you it's not here. In your case, so 4.8 compared to 4.63, the student gets it wrong. Then I give the student another task, what is 3.02 compared to 3.17. And here the student gets it wrong, right. So then you learn, okay, so here, given that the student got this answer right, it was not this misunderstanding.
Probably.
So, probably, exactly, yeah. Monty Hall is not lying. Okay, this is the point here. So this is something I can exclude. And the link is, I can probably exclude that the car is behind that door where Monty Hall says, let's open it. And there you see for sure it's the door.
You cannot open students.
Yeah, you cannot open the students. So here there's some limitations. But anyway, the point is, you have a priori three possibilities, and then based on new evidence, the probability space is reduced. You know this is no longer true. And now you update.
It's moved to a certain.
Yeah, I know, exactly. And the question is, can you use the tools that we developed, or we developed? This is Stefan, who is the spearhead here, and who wrote this paper, this brilliant paper, how to make students understand the Monty Hall problem, can you apply this tool, Hans-Jörg, perspective change, to your problem, namely once you can eliminate one hypothesis, how
But
this...
I can tell you, you can never exclude a hypothesis. A big difference to Monty Hall is, even if a student does not have a particular misconception, he still may make a mistake. Just for not being focused. Yeah? And this probability in your paper is given by 80%.
I give you this.
It's like Monty Hall opens the door and you see a goat, but it's only a goat with 80%.
You will never see a goat.
So it's more complicated.
Of course I know.
That's why I said one really has
Yeah.
to read the paper.
I know. Okay, good. I know this, what you're saying, you're right. Still want to make my point by saying just assume you give a student 1,000 different tasks and they all get these 1,000 tasks correct, or a given student get all of these 1,000 correct, so that you can eliminate the whole number hypothesis, because if the student had the whole number hypothesis, he would got all 1,000 right.
But then again,
Wrong,
the
but he
teacher
gets
wouldn't
all
give
1,000 wrong.
1,000 tasks.
Yeah.
And you can still...
But what you're alluding to, and realistically to, is that, of course, teachers can update several times. And we haven't investigated this. We intended to. We just asked, what about giving 2 or 3 tasks? We will do that in the future. But for getting any results in our context, we firstly excluded multiple cues on students, which we believe very interesting, but would increase the complexity. Because what does a teacher do when he combines information of several tasks? Does it do it?
We weren't sure whether then he would use for the second update the posterior as priors, or still consider the original priors and so on, in this setting. So we said for the very first study we want to exclude the more complicated setting with several tasks and only focus on one cue judgments. But we have plans.
I mean, the empirical basis has been rather small, and you had 46 students, teacher students, not pupils, and the pupils were invented pupils, and they were given, I think, 6 different tasks, 6 different problems that they solved in a particular way, and these tasks were chosen deliberately. And most of them were in a way that they were in alignment with 2 misconceptions and were contradicting one other one. And if, like you said, I mean, that would be a completely different setup. Give them 1,000 random numbers, then you would not have that control.
Yeah, of course, but your idea of giving sampled information, that's very interesting, because we gave non-numerical but single information. It's probability knowledge, which we assume. But how do teachers obtain this knowledge? Not by either by reading and or by guessing, but actually they have cases, and maybe they have experienced 100 students in the last year. And by this, they have a sampled information on the situation. This would be very interesting to give the information not by bars, but by sample tables, sample numbers, sample experiences. Would be also a very interesting direction to investigate.
So maybe to sum this now up, I made a few comments. The first was, it was pretty confusing. What is now the Bayesian? We sorted it out. I said, what's the practical relevance? I'm standing in front of one classroom. This is also okay. And now we focused on a Bayesian inference task, classification. And here my 3 comments were: first, reliability. This is about frequency. Then I said, natural sampling generate thousands of number comparisons randomly drawn, and then we can also see how many frequencies, how many mistakes each of these 3 hypotheses would make. This is again a frequentistic approach, and with the Monty Hall, that was also a frequentistic approach. After I can exclude, and I give you this, there is not an 80% goat, it's a clear goat, but again with the frequency approach, you can see how often would a given understanding would lead to an error, and if I now have very, very few cases where this error is made, I would say, yeah, maybe this is just sloppy and fatigued and so, but not really misunderstanding, right? So then again, with this frequency approach, you could say one of the three hypotheses could be eliminated, but this is again Monty Hall, a frequency perspective and a long run and how often would it be. So basically my approach would be, or my recommendation, if you continue this, do not have single case and dig deep, but try to get frequencies in how you deal with this task. So this is in a nutshell what I wanted to say. Good.
Thank you very much.
We continue.
Yeah, and if you have questions which have arisen now, please keep them, because we have a final discussion where we can also talk about these. Okay? Or any urging question? Okay. One thing we are going to do in the future is also
check whether the Zoom people have questions.
the Zoom people. Have you checked?
No, nobody says hello.
Okay.
Yeah, they were not given
No
the
hand
possibility
raising.
to unmute, and they were not invited.
I'm very sure they were.
Okay.
Okay. Yes. Okay. Just open. You control the chat too.
I control the Zoom people.
Okay. So, actually, one thing we are also going to do is giving teachers the opportunity to choose tasks. After having seen the result of one task, we can ask which would be the next task to choose to get more information. Also very interesting and very relevant for the context. But now, for now, we move forward to a second study, which is quite short, hopefully less confusing, and even does not contain real students, since we present a simulation study as a second example. Because when we investigated this constellation, we said we were going into analyzing information processing, but the only information we investigated was, thank you, was information on the left side, so knowledge about the likelihoods and priors. What we didn't do is we had no assumptions on the mental representations which the participants had on their probabilities. We had no assumptions on the way they process these mentally. And of course, the normative way they would calculate, but they don't have any numbers to calculate. So we have to ask, what are the internal processes we assume during this Bayesian reasoning? How could humans represent probabilities? How could they process them that this would lead to a Bayesian reasoning? There's much to do, but we do it in our second part of the presentation in a theoretical way and in a simulating way. So, first of all, we assume that non-numerical values are represented as magnitude. That is, magnitude is a kind of analogous internal representation, let's say a mental model of a continuous magnitude with bounded values from small to large. And these magnitudes represent a ratio, base rate, probability, so a value, a continuous value. And this is more than a speculation that this happens. Of course, there are many studies showing that humans do represent these kind of continuous magnitudes. For example, humans and apes can recognize relative size of bars, the ratio of bar lengths or dot numbers, and thereby have a mental model of magnitude. Or Bonn and Catlin show that humans are able to link these magnitude representations between different modes and dimensions. So ratio of lengths can be linked to the ratio of color, of loudness, of brightness. So actually there are many hints to the fact that humans can represent continuous magnitudes and use them for reasoning and for decision making. And in the case of probability, you could ask, how does that relate to probabilities? And there's a very interesting paper of Kevlani, in which he and co-authors posit that the sampling of cases can lead to a representation of magnitude. So 5 out of 10 cases or more can be represented as a qualitative magnitude and be used for further calculation. So to make this a little more visible, I'd like to present it in this figure. So here, for example, you see that when giving a medium-high prior, it's represented as a magnitude a little higher than half, or a very low likelihood can be presented like this. Okay. Secondly, what do individuals do with this representation? How do they combine it? How can they follow a kind of Bayesian reasoning? I'd like to present this to you in a interactive way. Here you see the same picture again. We have 3 hypotheses. Oh no, I want to have 2, sorry. Make it simpler. No, 3, sorry, 3. 3 hypotheses with this distribution. And now likelihoods for a certain evidence which has to be combined with these priors. So what would be priors only strategies? Priors only would mean you only process the prior information, and therefore when the priors change, the posteriors change accordingly, and evidence is simply ignored. What would be an evidence-only strategy? You only focus on whatever the priors are. You see, the priors don't change any decision, any updating, but the evidence does, and the highest evidence is considered as relevant, and the rest is somehow added to result 1 or simply ignored. When you combine evidence, of course, all 3 magnitudes of the evidence have to be combined and also lead to a posterior, which is close to the evidence. So this is easy. This is what we how we imagine that how we model that evidence only or prior only decisions are made. But how about Bayesian reasoning? Is it possible in this context to imagine what a mental process could be to combine correctly? Yes, it principally can. We will discuss that further, and could look like this. Let's look at the first hypothesis. You have a hypothesis of about 30%, and within this.
See the hypothesis in the triangle.
Okay, let's go from the beginning. We have 3 identical equi-probable hypotheses. The point of the triangle would be in the middle. Now we increase the first hypothesis, which means the point of the triangle is close to the first hypothesis at the top. This is the point. It should. We had done it like this, but sorry. Thank you for the hint. Yeah, we really tried to, but we missed. Now, is it on Zoom?
Yes.
Thank you for the hint. So, again, so you see a large large magnitude of the first hypothesis reflected here. The point of the triangle is close to the first hypothesis.
Wait, that means the larger the probability, the closer.
The closer to the vertex of the triangle.
Yeah.
Okay, so the probability on the vertical bar corresponds to 1 minus distance? Or?
Yeah, that would correspond to the distance to the opposing side of the triangle when you want to calculate. But when you do it intuitively, the closer, the higher.
So the point, upper left point in the triangle is the hypothesis,
Mm-hmm.
and the opposing side denotes the distance to the opposing side corresponds to the probability
Yeah.
that this hypothesis is true.
Yeah, but you needn't know. So
We need to know.
yeah, you didn't know when you're a participant. But now, as researchers, we have to understand.
The Hypothegon, I understood it as part of a hyperplane with the vertices in a three-dimensional coordinate system.
Actually, it's barycentric coordinates, and we don't go into the math behind it. But you're totally right. You can measure the size by the distance, but we can intuitively say the closer to the point, the higher the relative probability. We have a high probability for hypothesis 1 and a rather small likelihood for the evidence. And the question is now, can you imagine what the posterior would be? Of course, when you put it in relative frequencies, you say that a part of the population has misconception 1, and of this part, a part commits the error, would lead to the evidence as seen. So this part of the whole part is nothing but the likelihood magnitude as relative to the as relative to the prior magnitude, as part of a part. You know, again, the prior magnitude is a part of the whole of the certainty. The likelihood is a part of likelihood between 0 and 1, and the part of the and this is the part of participants, the part of subjects which commit this error on the condition that they have hypothesis 1, have misconception 1. So, geometrically, this bar, the likelihood bar, is put into the shorter prior bar as part, and what you can read of here is the posterior. Just multiplied proportions, as you get what to say. And this can be done for all 3 hypotheses. And now you have to combine these 3 posteriors and, of course, normalize and see them in relation to each other to reach the posterior distribution. And now we can play with it, what happens when the opposing likelihood is also small, and so on. So, we do not posit that people think like this. We just demonstrate that part of part thinking can be a way to achieve Bayesian reasoning within a non-numerical setting in a natural way by thinking part of part thinking. And this part of part thinking is not so exotic as you might think. Part of part thinking is very usual in curriculum. Yeah, I have to change again, thanks. Oh, I'm so thankful that you all...
Oh, because you changed the program.
Yeah, I have to change doubly. I have to change twice. So, last time, everybody sees. Yeah, this is right. This should be seen by everyone now. Yeah. Okay. This is an example for a task in a textbook, 5th class, for understanding multiplication of fractions. Multiplication of fraction is nothing but determining the part of a part. What is 2/5 of 1/4? And you can also use such external representations which support mental models for part of part thinking. A little later in curriculum, percentages. Yeah? Typical situation for students is calculating double step reduction. What happens if you twice reduce the price? Twice reduce to 75%, and it's also part of part thinking. And I used this authentic task from textbook to show you that authors use external representations that support this magnitude thinking and help to understand what is meant by twice reduction of proportion reduction of 75%. And of course, when it comes to probability, a little later in most German countries, you can also use this part of part thinking, which is nothing but the rectangle, the square, and which represents the part of part thinking connected to multi-step probabilities. Okay, so what we don't know is that what we can expect from our students? Of course we can't. We do not think that that school teaching these representations really leads to a to a long-term knowledge and a mental representation of part thinking. This is maybe done in school, maybe it isn't. We do not assume that this is the normal way people think, and so it is also not the way we expect that Bayesian updating works. Just activate your school knowledge about parts and everything's okay. Won't happen. So it's still complicated. It's possible. It's mentally imaginable, but it's still hard. And even worse, in the case of our Hypothegon, we do not assume that our successful 10 students, teacher students who applied Bayesian reasoning did this. What did they do? Remember the situation where they see the bars, these likelihood bars, which we represent the size of the priors, is nothing but doing this multiplication explicitly, but to judge and to give a decision, they just have to read off. So it could be possible that our students did nothing but read off the lengths and use this by a kind of intuition, the right answer, and not do a mental model manipulation internally. We do not assume this. We cannot.
We call it an as-if model.
An as-if model. It's a nice name. Yeah. We call it pseudo-bus, pseudo-BUS, because it looks like Bayesian reasoning, but it isn't. Reasoning does. This is our question. How far away is it? We try to investigate this first by simulation. We try to analyze the data we had in our experiment. We couldn't see whether any of these students used this additive strategy, except for some cases in the Think Aloud interviews, but the results were too close, so we couldn't distinguish this APES strategy, as we call it. APES as averaging priors and evidence strategy. APES wasn't detectable in our data, so we either had to do a new study, empirical study, or, which we now present, a simulation study. This is our second research interest. Can additive strategies really be seen? And therefore, we first reduced our complex situation. We don't investigate the three hypothesis situation, but only two hypotheses. The normal one, which you all know, disease or healthy, or misconception, no misconception, so only two hypotheses. And we then can simulate the results of either correct Bayesian reasoning or the approximative APES strategy. And we ask, how plausible is this APES strategy? And can this strategy suffice in certain situations? Is the strategy sufficient for deciding in certain situations and not less good as proper Bayesian reasoning? So in this example, as you can see, for certain situations, certain configurations of the situation, when there are certain probabilities and certain likelihoods, this results in a quite similar decision, quite similar judgment when you look at the position of the point. Now we have a one-dimensional hypothegon, so just the bar which says, are we on top hypothesis 1 or on the bottom hypothesis 2? Okay. So we ask, are these strategies plausible, cognitively plausible, and are they ecologically rational? There is lots of empirical support for such additive strategies. It's not just two participants of ours who had this, but we see it down to 1975. Many studies in which participants use for sequential judgments, for combining probabilities, additive strategies. They add instead of multiplying. Or taking average, for example, Chanteau, where when neutral evidence is presented, where we should not change, when the likelihoods are identical, we should stay with our priors. Instead, they combined priors and evidence and went in direction of evidence, suggesting such an additive or averaging strategy. For example, Cohen and Staub, who investigated the Bayesian reasoning intra-individually, asked what are the strategies within one individual, in many cases, fitted such a model of combining the data in a linear way, and found that for many participants there is we have a combination, a regressive combination of the values, of the input values. However, they don't give a cognitive explanation what happens when these data result. Or, for example, Jocelyn has a very interesting situation in which participants have to decide whether a part in the production line comes out correctly when every single step in the production line could produce an error. So it's about error multiplication. And they find that very often subjects do not multiplicate but add or take averages. They only multiply when the situation is very simple, when it's two rather simple values. Of course, all these studies are numerically. It's about numerical determining the posterior or the combined probabilities. We ask whether this is also plausible when there are no numerical values. So, however, how accurate is this strategy? And we reduce to not giving posterior probability, but to decide. We only ask, is the decision correct? Not is a probability value, is a posterior close this, because there is no calculation. There's simply the question, will I decide to go to hypothesis 1 or 2? We do this for 2 hypotheses first, and later on, quite shortly, what happens for our case of 3. Our simulation explores the whole hypothesis space, meaning high and low values for the 2 competing hypotheses. We use likelihoods in a broad range between 10 and 40%. When likelihood is 4 in favor of a hypothesis, and we chose the likelihood against hypothesis in this configuration against hypothesis 1 in favor for 2, because the other way around would result in the same data for a case of symmetry. And now we ask, we simulated the decision. So, prior only decision would be which prior is higher. This would be my decision. Evidence only, which is the highest evidence, I switch to or keep, or I decide for the hypothesis with the highest evidence. Bayesian reasoning amounts to combining both and comparing both. So we don't need to calculate the posterior, we just combine, multiply the 2 prior and evidence. It's part of part, nothing but part of part thinking and comparing. And of course, apes then results in adding, or is the outcome of Bayesian reasoning. When we simulated normative, correct Bayesian reasoning. Each dot, gray dot here, represents a single judgment for a certain set of parameters in probability space. So, for example, when we are at this point, it's 90% for hypothesis 1, 10% probability of hypothesis 2. And now, going through all values of likelihoods, this produces all the dots in this region. Every dot says a decision was made, and the y-axis, the value, is nothing but the posterior value, meaning the accuracy of the decision. When I've decided for hypothesis 1, the question is, am I correct? And of course, I'm not deterministically correct. I'm only correct with the probability of the Bayesian posterior. Yeah? And this is always higher than 50% because I decide for the higher of 2 probabilities. So you see, let's go through it. In this region 1, we are beginning with hypothesis 1, and the posterior still is for hypothesis 1. The posterior again, the likelihood against does not influence. We have still a decision for hypothesis 1. In this region 2, the hypothesis is more probable, say 90% for hypothesis 2, and the evidence also goes in this direction. So it's clear that I will decide in this direction, and this results in a good decision. Only in this area 3, the posterior and the is not as high because priors and likelihoods combine and compete. So it can be that the one or other is closer, and I decide for the one or other. Actually, for teachers, one would say better do not decide when it's so unclear. When you have competing combinations of evidence and priors, do not decide in this region. But still, if I do it algorithmically, I'm quite good. But this is not our question. Our question is, what does apes do? Just to increase the yes, I hope this was rather clear. It's one of the figures which is not quite intuitive. But what does happen when we simulate prior only or evidence only? The gray region, which you see here, is still Bayesian reasoning. So this would be the best decision according to normative Bayesian reasoning. And the colored dots are the result when either ignoring evidence using priors only or ignoring priors using evidence only. And of course you see then you commit serious errors leading to correct decisions which are the complement to the decisions according to Bayesian reasoning, go down to 10% in certain regions. But now let's look at apes. Is apes an improvement to this? Or is it much worse, or is it only a little worse than Bayesian reasoning? Let's see. The results look like this. And as you can see, most of the decisions are equivalent, are exactly the same as Bayesian reasoning. It's only a very small area which only deviates to a small value from Bayesian decisions. That is, only when the posteriors are in this zone of ambiguity, it deviates to a value smaller, and for most of the other values we hit the right value. And this seems cognitively plausible, refers to the fact that averaging can be very successful, and also is mathematically plausible, as I can show you here. This is not human thinking, this is mathematical argumentation. This would be the correct comparison to decide due to Bayesian reasoning. Just compare the two posteriors to combined joint probabilities. When using priors only, it's kind of only use the one dimension, only use the prior values, so one line, or only use on the vertical likelihood values. And when doing apes, it's just adding or averaging the two, which amounts to calculating the circumference. So what we do when we do apes mathematically is substitute the complicated multiplication procedure with a much easier circumference estimation, let's say. And this is, of course, for the math teacher, horror. And we've got all students confuse the two, area and circumference. But for deciding which area is larger, for most of the areas, or most of the value, the decision which is larger is identical when using circumference instead of area. It does not work when it's extreme, as you can imagine. So, there are many reasons for apes, and we also looked into what happened, don't worry, we don't go in this much deeper, also looked what happened when we did it back to three hypotheses. This is also a simulation. We explored the whole hypothesis space, all combinations of three hypotheses. We used values, but we only displayed the values of precise likelihoods, otherwise they would be cloudy, you can't see anything. The bird somehow rises, the bird, we call it the bird, sorry. The figure rises or sinks a little bit, but mostly you see no deviation, except for this region, the region 3, where actually apes is much less good than Bayesian reasoning, and this is the region of ambiguity when we have evidence that is accords to two hypotheses, so you can't decide. Whenever the comparison of this product are close, the decision is not good. This could be said is our main result of this simulation. So we state that apes is a very good approximation for most values of priors and likelihoods when only decisions between hypotheses are required. We do not posit this when it's about estimating the correct posterior, so we did not investigate this. And it's ecologically rational for teacher decisions because you don't want to know what the posterior is, but whether you should or not should go in this or this direction when deciding on a student. Actually, even evidence only is ecologically rational. You see an error and you go for it. It's not bad when it's not about giving grades, but about asking again or by talking to the student. It's not a bad thing to go for the evidence in this case. The context of teacher acting is quite complex. Yes, of course, we need further empirical support for it. We really would like to go with it also empirically, which is reasonably done. And just to wrap it up, finally, the two studies we presented, we have investigated Bayesian reasoning and apes and averaging priors and evidence as both cognitively plausible, but still Bayesian reasoning is cognitively plausible, but still hard to do. Part thinking can be taught, maybe, let's see, but it's not a natural way. Apes, on the other hand, is kind of a primary heuristics, very natural to do and available without instruction. And of course, we'd like to find out whether we can substantiate this, whether we can trigger apes or not need to trigger apes. We want to know if external representations support it in a more or less natural way. And if we can test for it, really show it in a way distinguishing it from other strategies. So our final question is, can we support the bus non-numerically by applying part-of-part thinking with and without representations? And we like to end with a note. You see this picture we found. It's very nice because it's a bus which needs support. And when you look in the right corner, bottom corner, it's even the ensemble, playing ensemble, its name is ABC. And for this we thought this is a CD with Baroque music, very nicely played, and we really, Laura, want to thank you for inspiring us kind of to all this kind of research by giving to you in this CD, ABC CD, supporting the bus. Thank you very much.
I think before we go into lunch, we have a discussion here. And let me start with a comment. And I have to admit, now I am a bit confused here. And I mean, we may all have heard about that research that tells us that apes are about as good at the stock market, as successful as experienced stockbrokers. And that's what I thought about when I heard you talking about your ape approach. And what confuses me is we have that well-founded, mathematically well-founded Bayesian approach with a formula, and then you have something else, that ape approach, and I cannot see any rationale in it. Why should I go there? Okay, you showed us. I liked your Cinderella illustration, yeah, and I took from that the pictures look quite similar. So, but I don't understand why, and I also wonder if they also correspond point by point, and not just as the whole set, yeah, and that whole set. And again, sorry if I sound a bit ironical. To me, the picture looked like a Narrenkappe, yeah, like a tool's hat. These two, yeah.
Sorry.
So I'm still a bit confused. What's the main message? Do you think ape is more intuitive than Bus? Okay.
So
you have to convince me, or I have I need more time to think about it.
So from a math education point, this is horrible, because obviously apes is wrong. It's not what you want students in school to learn, how to solve Bayesian reasoning tasks. But as a heuristics, if you have to decide quickly, then really this part thinking that is required by Bayesian reasoning is very difficult. What is, I don't know, what is 3% of 57?
Okay.
You can't answer this quickly, but you can quickly decide what is the middle between 3 and 57.
What did you just say? You can quickly decide.
What's the middle between 3 and 57? It's very natural, but what is the product of 3 and 57? Ask any of your students.
But I mean, to me, the ape approach reminds me of the famous Kapitänsaufgabe in Mathematik. You have some figures, and you have a prior and a likelihood, and you just have to do something with it. Why not adding them and comparing them?
Actually, this does happen. The studies which I presented in a numerical context, in which students had to solve multiplicative tasks and actually did additive or averaging tasks, we are very aware that it's most probable that they did this for simply doing anything. Yeah. Here are two numbers. Do something correct. I don't know.
I have no idea, so I add them.
Yuslin says those students who actually multiply somehow seem to have remembered from their math lessons that probability have to be multiplied. So when we put it bluntly, which we investigate as strategies, maybe curriculum, maybe curricular experience. And what we are not like to go into is to create situations in which this experience does not play a role. When there are no numbers, you cannot apply strategies, you cannot apply long-term build heuristics you learned in school, but you have to do something mentally proper. So, and what we posit is Bus can be done mentally proper, but is still complicated. It's multiplying, comparing products. And it is very reasonable to do, not because it's wrong, because it's sufficient for many situations. And when we do this, we have good results. So we don't say that teachers do this, but generally it would be interesting.
Because if you say you have a high prior probability and a low likelihood, or the other way around, you say, well, these compensate, so it's somewhere in the middle. And you answer this without doing the calculation of multiplication. You see it, oh, this is high, this is low, so the posterior is somewhere in the middle. So this is very intuitive, and that's what students told us what they were doing in our non-numerical environment. And so we said, oh, well, that's interesting. And then we went and looked into the literature and saw, well, there are many hints that people do this.
So who we know has...
Come here.
Yeah.
More questions, more comments. Stand up.
So, yeah, there is this guy, Peter Yuslin, and I admire their research. They're sweet. And as you see here, what this is suggesting is that there are Pi mal Daumen things that students do, and we do probably also, which are good enough for perhaps surviving, for estimating if you tested positive or something. Do I have to go to the hospital? Things like that. So I admire this kind of work, as we admire also Peter Juslin, because it's this Pi mal Daumen Regelung, which works good without multiplying, without doing parts of parts of parts, but we do have a minimum of estimation. So there is a minimum of psychological estimate. Is it? So do you think this can be taught, and do you think this can be generalized?
As Katharina said, maybe this shouldn't be taught in school.
In school, not in school.
Yeah. With respect to certain situations, first we'd like to understand whether it's already done before we try to instruct. Any kind of instruction for us would not be to optimize behavior, but would be to detect, to experimentally create situations in which we can detect that this is possible. Maybe certain external representations trigger this kind of thinking. Maybe we are at a very basic question of when do people represent probabilities in such a magnitude way. This could be asked by taking apes seriously. And we're far away from knowing according to Simon, which are the two blades of the scissor, which situations, which heuristics fit together. We are on the first step on a long journey.
Okay, I have one more question. You said, it is ecologically rational, because you're apparently thinking that there is, the environment is playing a role. Yeah, so can you explain that further?
No, simply quick decision. When we have two values, how high and low values, or 4 in our case, or 6 even, how do we combine them? And when you have to do a quick decision.
What is the ecological aspect of that?
The ecological is that we can be successful when deciding in this way, whereas cannot give any good decisions when we don't have the heavy heuristics. So. But we don't say that we know the ecology in which this happens. Okay. There can be many ecologies in which it happens. And teacher is only one which may be too far away.
Yeah. All right. Here again, I think that we have. Yeah. Oh, you have a question? I'm sorry. No. Read your comment.
So I want to share an observation or have a comment. So when I analyzed the data of this Hofrage 95, so we had 1,800 sheets of paper where I analyzed the strategies, and you do not believe how creative students can be to do something with 3 numbers. I think I identified something like 40 different ways to manipulate this and to integrate these 3 numbers. One is the Bayesian way, this is correct. But then there were also interesting shortcuts. This is what you now said, no? Call it heuristics. And a shortcut is, for instance, the big hit rate shortcut, and we have this in our paper, right? Typically not so much attention is given to this. But I also found it quite interesting. Another one, and this is, I think, a shortcut that often makes sense. You just divide the base rate through the false alarm rate. Base rate divided by false alarm rate. And if you look at the formula, if you have a high sensitivity, this is in the numerator, whether you multiply with 95 or not, that doesn't make a difference. And if you have a very low base rate, then you have a big complement. And here the false alarm rate is all what matters, and this 5% false alarm rate multiplied with 95, forget it. And then, so in many tasks, base rate divided by false alarm rate will do a good job, and this is an ecologically valid or rational shortcut. Then there are others. And now, a comment on these others. And here I want like to look at the linear equation you show on page 50.
do we need? No, I think we don't need this. So this is alpha times base weight times beta times hit rate times gamma plus gamma times
force hit rate.
No? Good. And earlier, some minutes earlier, you said, yeah, like we don't think that people do it, but if there is something going on in the head like, and I have been throwing on in our ABC community or world, this is called an as-if model. And now interestingly, you can also treat this regression as an as-if model, and you could try to model someone who is solving these tasks and see what's the fit of this model. And now I can tell you, and this is, I think, yeah, I'm pretty sure about this prediction. If I consistently use Bayes theory and you model me with this equation, you will find this model does better than chance. Why? It's very easy. The hit rate is in the numerator.
Yeah.
That's what the Bayesian formula suggests. Across many problems you will find there's a positive correlation. The higher the base rate, the higher the posterior. The higher the hit rate, the higher the posterior. The higher the false alarm rate, the lower the posterior. So alpha positive, beta positive, gamma negative, I can tell you without having looked at one single number. I've never done this calculation, but it's intuitive. You can understand it. And then you could say, this guy is not doing Bayesian reasoning. I do not even know what this is. I just, because you do not know it yourself. You only have your Bayesian, your regression, right? For a hammer, everything looks like a nail. And for a person who likes to have regressions, everything looks like a regression problem. He observes me. He's doing regression, significantly different from zero. So that is, if I'm using Bayes, you regression guy will say, yes, he's doing regression. And can we turn it around? If the regression is significantly different from zero, do I do Bayes? Okay.
No. So, well, first of all,
and this is what we call maximum and strategy identification. And of course, these tools may be correlated. They may give hints, but still, I would say careful, and you have to consider the possibility, what would other tools do? And then we are exactly at your first part of the talk. Maybe if someone else models me with Bayesian, then he will find a perfect fit. You will find a semi-perfect fit, right? And then the probability that I'm using Bayesian is all on the side of the Bayesian model.
So first, the regression wasn't by us, but by
I know this stuff.
So we didn't use that in our data. But what Timo mentioned, and which completely fits to your point, using the ape strategy or using Bayesian reasoning ends to decisions or even to posterior that are so close together that you can't tell these two strategies apart.
Not by regression.
Not by regression.
And you understand why if you look at the equation?
Yeah, and you have given a cognitive explanation why this regression result is plausible when doing Bayesian thinking compensating. You gave an explanation how the function, the posterior, is monotonous in the arguments. And this is exactly what we also showed when we said that when we reason mathematically why it's reasonable to do this, why it's a good approximation. But when it comes to finding this as an explanation on the level of mental modeling, then we have to do much more close investigation on real distinguishing. And what we did with our Bayesian classification in our first study is possible to do with apes and bus when we design an situation, an experiment in which the data, the constellation are real in a way that we can begin to distinguish and not argue ex post what may have happened. Of course, this would be the next logical step to combine the Bayesian classification with a good experiment that may distinguish between the two strategies.
And this also answered the question that actually Joachim posed quite some time ago, whether it's the posterior or the decision, what is similar between Bayes and both. Because what we showed is only the decision. And then we say this is a very good heuristic if you just have to decide and not to give an answer concerning the posterior. But because we want to detect and separate apes from both, we also looked at the posteriors for many, many constellations of priors and likelihoods in a systematic way, and we found the distance between the posteriors usually isn't big, and there are like only very few constellations of priors and likelihoods that we see a chance that maybe you can tell these two strategies apart, and therefore if we want to tell them apart, we need to design the study in order to do so. So yes, apes is good for the decision, but it's also quite good for the posterior in most cases. So that probably answers your question.